The question that I have is, could you do an example on friction involving rods? Let's work on this problem. We have two rods, AB and BC, connected through a pin at point B. Point B is subjected to a vertical force F. The coefficient of friction between the rods and the floor is 0.5 and we are to find the value of theta. Note that in this problem, they have not given us a value for F, the force that is acting at point B. Do we need it? So let's go ahead and solve this problem and see if we can find the answer to that question as well. We know that the connection between the two rods at point B is a pin, right? So what we have is a small truss, right? So we could either use the method of joints or the method of section. Let's go ahead and use the method of joints. We also recognize that there is symmetry about the vertical line passing through point B, right? Let's take advantage of that also. Just as in a truss, the members AB and BC are two force members, right? Therefore, the internal force on these members are just axial force. If I call the tension in rod AB as T, it has to be the same on rod BC because of the symmetry we just talked about. Similarly, the reactions at point A and point C must be identical. We will consider the free body diagrams at point A and point B in the analysis. Here is a list of the unknowns of the problem. AX, AY, T, F and theta. There are 5 total. In general, you could write down 2 equilibrium equations per joint in a truss structure, right? So there are 2 equilibrium equations available to us at joint A. However, at joint B, when we mark the tensions in these rods as equal to each other, we already took advantage of the symmetry about the vertical line. And therefore, you can only write down 1 meaningful equilibrium equations at joint B, which is the force equilibrium equations in the vertical direction. Finally, we can write down a friction equation at joint A, and therefore we have a total of 4 equations available to us. But including F, there are 5 unknowns and therefore it cannot be solved. So let's go ahead and investigate this further and see what's going on. So I'm going to start with the 2 force equilibrium equations written for contact A, and here they are. Now dividing equation 1 by equation 2, I get this equation. Remember, we are solving this problem at the state when the rods are about to slide at contacts A and C, right? And therefore, the friction law must hold at contact A, which says the shear force must be equal to mu multiplied by the normal force. Mu is given as 0.5, and therefore AX is 0.5 times AY, and from that we get this equation, which says the ratio between AX and AY is 0.5. Now we have 2 equations, equations 3 and 4, for the ratio between AX and AY. This one says the ratio must be equal to 1 over tan theta. This one says the ratio must be equal to 0.5. By equating the 2, we can find a value for theta. So I get a value of 63.4 degrees for theta. So let's pause for a second and see what just happened here. We just answered the question. The question was to find a value for theta, right? We only had to use the equilibrium equations for contact A and the friction law in order to achieve this. We didn't have to use joint B, and therefore the force F never entered into the formulation up until this point, right? So what we are finding here is that the minimum value of theta that can be sustained without sliding at contacts A and C is 63.4 degrees, and this value is independent of the force F that you apply in the vertical direction at point B. However, the magnitude of the tension T on these rods is going to depend on the magnitude of F, and we can find a relationship between F and T by considering the equilibrium of the free body diagram for joint B. So let's go ahead and do that as well. So here it is, the force equilibrium equation written for joint B. That leads to this relationship between T and F. T equals minus 0.56 F. Since we have a minus sign here, it's obvious that the force on these rods is a compression. We could have guessed that from an intuitive point of view. In other words, you're pushing it down and therefore the forces on these rods would definitely have been a compression, right? So if we have a value for F, we can use this relationship to find the compressive force on the rod. For example, if F is 100 pounds, then T would be 56 pounds compression, right? Another interesting thing to note here is that we didn't have to use the actual linear dimensions of the problem. In other words, these solutions are independent of this vertical distance and this horizontal distance.